created a Desmos for you. It's on Blackboard if you go into the Unit 2 folder, right, under calculator. So calculators, then Unit 2. It should be right there. It should say linearization or linear approximation. I can't remember. I can actually look real quick. It's my attendance roster, so that doesn't help. Calculators, Unit 2. It's linearization. All right, but then when you click on it, it says linear approximation. So I guess it's both. All right, so I'll bring it up here just so you see. It's what we worked on last time, but I cleaned it up a little bit, and by a little I mean a lot. Right. Not a problem, Matt. All right, so find a linear approximation to the function at x equals 5. Really just boils down to a few key steps. One is evaluating the function, but also finding the derivative of the function at the point. And this is, in theory, the nice number, right? They selected the nice number for us. So sometimes we'll have to do it, they'll do it. Sometimes, it's kind of a combo, right? It depends on the nature of the situation, right? So if we're doing it by hand, we'd have to find the derivative, but I'm actually not always going to, you saw in the practice test that it called for you to find the derivative, but I'm not always going to require that, right? So you just got to, really fight the battles that need to be fought, right? But let's just assume that the directions are saying that you have to find the derivative. There's no expectation that you would simplify or even actually use that derivative to do the computations, but we have 3x multiplied by e to the 2x minus 10. So we have the first function, which is 3x, and my second function, which is e to the 2x minus 10. All right. So my first function, 3x, so first would be multiplied by the derivative of the second. Now, just as a reminder, a little refresher, derivative with respect to x of some function e to the u is e to the u multiplied by du dx, where u is the exponent of that exponential function. So when I take the derivative of e to the 2x minus 10, it's going to be e to the 2x minus 10 multiplied by the derivative of the exponent itself, because that's a linear equation or a linear expression, I should say. The derivative of that is just a 2, right? So plus my second function, e to the 2x minus 10 times the derivative of the first, which is just a 3. All right. That being said, maybe you don't even need to do that, right? You certainly don't need to do it in order to find the derivative at x equals 5, because for that, you could plug in if you want. I'll plug in, but I could also show you on the calculator, the Desmos calculator, the linear approximation linearization. You just type in your original function, 3x e to the 2x minus 10. You just got to be careful. So when you put in an exponent, sometimes it'll just take the first term and make that the exponent, and then try to make everything else just ordinary font. So put in parentheses 2x minus 10 to keep it associated with the exponent. It's kind of weird. What I do after the fact is I just erase the parentheses because I think it looks a little nicer, but that's not a requirement. Right. A nice value here would be 5. That's what they told us. We can get it to land on the 5. And then, I can go with my ordinary zoom here. That's what the graph would look like if you're interested in that. But f prime of 5, I just scroll down. It'll give you the linearization model, which is wonderful. But f prime of 5. Oh, is that like literally the one thing I didn't put in here? Okay, well, I'll update the Desmos, but you need f prime of the a value. So I'll just tuck it in, I guess, here. So f prime of a. All right, so that's going to be 33. All right. I'll actually refrain from writing that down for a sec, because if you did it by hand, the reason why we select a nice value is because in theory it should kind of clean up nicely. All right, so 3 times 5 times e to the 2 times 5 minus 10 times 2 plus e to the 2 times 5 minus 10 times 3. All right, the e to the 2 times 5 minus 10 is really e to the first, e to the 0th power, which would give you a result of 1. So these parts would cancel away. And so 3 times 5 times 2 is 30, plus 3 would be equal to 33. So even if you did it by hand, it wouldn't take a whole heck of a long time. Right? We also need f of 5, which actually would be even easier to do by hand. But that I actually did have the foresight to plug into the Desmos. Right? So that's just a 15. But if you wanted to, again, you could just plug into the original function. It's not too bad. F of 5 is going to be 3 times 5 times e to the 2 times 5 minus 10. This would cancel to a 1, and you'd be left with a 15 that way. All right. So my L of x, my linear approximation model, is f prime of a. So f, well, I'll actually write the formula. F prime of a times x minus a plus f of a. Right. So that's the rule that we're going with. Oh, that's not a lasso, by the way. Anybody was wondering what the heck I was doing there. So L of x would be equal to 33 times x minus 5 plus 15. All right, so that would be my linear approximation model. All right. So the 33, we get that one of two ways. One way would be just by typing in f prime of 5 in the calculator. The other way would be to replace all the x's in my derivative with a 5. All right, so every instance in which I put the 5 in for the x in the exponent gave me a 0 as a result. 2 times 5 is 10, minus 10 is equal to 0. So this whole expression here and this expression here would go to 1, right? Because e to the 0th would be equal to 1. So 3 times 5 times the 2 here would give me 3 times 5 is 15, times 2 is 30, plus a 3 would give me a 33. So that's the linear approximation. We're not asked for this question to do anything with that information. We're just asked to come up with the equation. So it's really not too bad. Right? But you'll see in the upcoming problems that we do have to do a little bit more. But for something like number 2, h prime of t, much simpler. It's just power rule. So 4t cubed minus 18t squared plus 3. They're saying to do our nice value here is -3. Doesn't seem very nice, but it is what it is. Right? So h prime of -3. So what I would do here, again, use Desmos to my advantage and let it do the crunching for me. Except we'll put it in terms of x, but probably used to that by now. All right, so this would be my original function in terms of x. And then my nice a value would be a -3. Doesn't always want to land on it in the first shot. All right, I put my f prime of a there. That's going to be a -267. Now the numbers are a little crazy, but at -3, we're going to have a point of tangency that's somewhere up here, right? So that's a y value of 227. All right. So if you want, you could just zoom out a lot until you see the point of tangency and then just bring it back in. All right, but that's negative 3 comma 227. So that's what h of 3, negative 3 would be. And those are the two pieces of information that I would need. So my linear approximation model is negative 267 times x minus negative 3, right? So x plus 3 plus 227. All right. Now, we just have to make the transition because that's in terms of x. So we'll just change our x's to t's. Or you could just kind of skip right to the step, but that would be our linear approximation model. All right. So then we get to the whole point behind this stuff, numbers 3 and 4, which ask us to actually use the linear approximation model. Right. So find a linear approximation to the function g of z. Right. So change it up to variables again at the fourth root of where g of z is equal to the fourth root of z at x at z equals 2. I see x. To approximate the value of these other two numbers. Right. Because when it comes to fourth roots, I mean, we could pick a nice value, but that nice value is not going to be anywhere near these two numbers. Right. So the first nice value would be 1. After that, it would be 16. So 16 would be kind of nice for the 10, but it wouldn't be very nice for the 3. Right. So we're going to work with this, but it's okay to have an answer that's in radical form. Right. So g of z is z to the 1/4 power. So g prime of z would be 1/4 z to the negative 3/4. All right. So at that nice value, g of 2 would be 2 to the 1/4. G prime of 2, not going to be much better. 1/4 times 2 to the negative 3/4. All right. Now we can, I mean, cleaning up is kind of a relative term. We can try to clean this up a little bit, but the only cleaning that we'll be able to do is moving that 2 to the 3/4 down to the bottom. So 4 times 2 to the 3/4 power. That's really the best we can do here, right? So then when it comes to our linearized model, instead of, again, L of x, we could jump right to L of z, which would be the derivative at 2 first. So that would be this. Times x minus our nice value. See, I put an x again. Z minus our nice value plus 2 to the 1/4. All right. And so when it comes to evaluating this for the z value of 3 and 10, you know, we're going to get an answer that's got some radicals in it, but that's not a big deal. All right. So I'm going to take this and I'm going to substitute in a 3. So L of 3. Now, when I put a 3 in here for z, that's going to make this a 1. That's actually not too bad because that's going to clean this up to just 1/4 times 2 to the 3/4 plus 2 to the 1/4. And there's really no point in going beyond that. This is compared to the exact values. We'll look at it in a minute, but, you know, I mean, in terms of going any further, it sort of defeats the purpose. You know, if we go to decimal form here and evaluate it in the calculator, then it's like, well, why didn't we just compute the derivative at that point in decimal form based off of the technology to begin with, you know? So, and then by extension, the linear approximation, and then, you know, for that matter, why didn't we just figure out the fourth root of 3? You know, so having it in this exact form, even though it's not a decimal, it's okay. All right, so L of 10, we'd replace the z here with a 10, so that would make it an 8. 8 multiplied by this, 8 over 4 would be a 2. So this one actually cleans up a little bit nicer. So we would have 2 over 2 to the 3/4 plus 2 to the 1/4. All right, because again, if I put in a 10 here, 10 minus 2 is 8. 8, 1/4 of 8, or 8 divided by 4 is 2. So I'd have 2 over 2 to the 3/4, but I could even go further with that, because 2 is thought of as 2 to the first power. Keep the base, subtract the exponents. You get 2 to the 1/4 plus 2 to the 1/4, which would be 2 of those 2 to the 1/4 powers. All right, so you get a little more concise way of representing it. You know, is it necessary to go that far? Maybe. Because you can see in the practice test that there are some questions where you go through the process and you get an answer, but then you got to do some algebra in order to get your answer clean to the point where you can evaluate, or where you, I was going to say evaluate, but I guess that works, where you can distinguish between the choices and decide which one is the correct answer. Anyway, but when it comes to actually figuring out, you know, the comparison between these and the exact values, that's easy enough. You just put it into the calculator. I'll just do the second one. So 2 times 2 raised to the 1/4 power would be that, right? As opposed to if I plugged in a 10 and raised that to the 1/4. You know, it's not really that close, but then again, 10 isn't really that close to my nice number of 2. You know, so if I tried the other one, I guess I can do it. The other one was 3 to the 1/4. Compare that to that funky fraction that we came up with, 1 over 4 times 2 raised to the 3/4 power. Plus 2 to the 1/4. You get something that's right there in terms of being a pretty good approximation. Right, so 1.316 is what the correct, quote unquote, correct answer would have been. We came up with 1.338. Right, so they wouldn't round to the exact same answer if you went out too far, but it's pretty close. Right, so it's not too bad. Right. So number 4, find a linear approximation to the function. Linear approximation to the function f of t is equal to cosine of 2t at t equals 1/2. All right, t equals 1/2 is a nice number because if I plug in a 1/2 for t, I get cosine of, actually, it wouldn't be a nice number. Yeah, cosine of 1 isn't really anything. That actually, I don't even know what that was. Yeah, it's really just going to give us an answer that's similar to the previous one, where you're going to get an ugly looking answer, but it'll be a pretty decent approximation. Yeah, if this were like 0 or something, that would be a nice number. Right, so they boxed this in. They said, okay, you're not getting a nice number for this one. You're just getting what you're getting. Right, and that's fine. So f of t cosine 2t, f prime of t, derivative of cosine is negative sine, so negative 2 sine 2t. going to evaluate each of these at 1/2. So I plug in a 1/2 for t, I'm just going to get a cosine of 1. Plug in a 1/2 into my derivative, I'm going to get -2 sine also of 1. All right, not pretty, but it'll do the job. So L of t, plug in my derivative value, -2 sine of 1 times x minus 1/2 plus cosine of 1. All right, so now I just have to evaluate my linear approximation model. All right, so it says cosine of 1 and cosine of 9. All right, so the issue that we kind of run into here is that since there's a coefficient to the t inside the cosine model, if I were to just plug in, if I wanted to figure out what the cosine of 1 was just based off of this, if I said cosine of 1, I'm really figuring out what f of 1/2 would be. All right, so I have to figure out what L of 1/2 would be. If I wanted to figure out what the cosine of 9 is, using this function, I really have to plug in a 9/2 to that original function in order to get offset by the 2 that's already there, in order to result in a 9 inside the cosine function. So I'd have to determine L of 9/2 in order to get a good approximation. All right. So what'll end up being the case is that if I plug in a 1/2, and I did it again, you see how I put the x here? I mean, the common answer to that would be, well, just stop using other letters. But the problem is the universe doesn't work that way. You know, in physics and other science areas, they use different letters besides x to represent different things, different variables. So we have to make that adjustment. But anyway, if I plug in a 1/2 for t here, all of this stuff is going to cancel out. And I'm just going to be left with a cosine of 1, which doesn't tell us anything. All right, it actually tells us that the answer to what cosine of 1 is equal to cosine of 1, right? Which is really just kind of an illustration of why when we're trying to evaluate a function using the linear approximation technique, we choose a nice number that's near the one in question. We don't choose the number itself, because then something like this will happen, right? And you end up going around in circles, right? But if I plug in a 9/2, 9/2 minus 1/2 is 8/2, which is 4. So I get -8 sine 1 plus cosine 1. All right. So in a matter of speaking, we kind of are living in a in a time loop here, because in order to be able to figure out what a cosine value is for specifically cosine of 1, we need to know what cosine of 1 is. In order to figure out what cosine of 9 is, we need to know what sine of 1 and cosine of 1 are, which is really the reason why we're here to begin with. So what this is telling us, aside from the comparative approximated value, and honestly, this is a typo. This shouldn't even be here. It's telling us that we went into, well, we know we went in a big circle, but it's telling us that the nice number, the quote unquote nice number that was selected, is insufficient, right? So it's not a good selection, which is why when I first started going over this problem, I was like, oh, the nice number of 1/2. Oh, wait a minute, that's not a nice number, but we played it out anyway because it's a good learning experience, right? But then number 5, that's where we're left to our own devices, where we've seen nice numbers in action and we've seen not so nice numbers in action. All right. So it really kind of drives the point home of like when you're going to select a value, you want to be very cognizant of what constitutes a nice number. So I'm looking at that e to the 0.1, and I'm thinking that that was the result of evaluating some function when the x value is equal to 0.1. That function itself would have been e to the x, all right? Now, what we want to do is choose, we had a not so nice x value here. All right, so this is not nice. So the nice x would be equal to, when you think about an exponential function, anything raised to the 0th power is equal to 1. Anything raised to the 1st power is itself. I mean, 0 is really nice because 0 is close to 0.1 and also give us a nice result, overused term, for the exponential function. So then what I would do is I'd find the derivative of exponential e, which is e to the x, also nice. Evaluate my original function, f of 0 would be equal to e to the 0th, which is 1. F prime of 0 would be also e to the 0th, which is 1. So L of x would be equal to 1 times x minus my nice number. That's our a value. So x minus 0 plus 1. Simplified, L of x is equal to 1 times x plus 1, so just x plus 1. So then all I'd have to do is evaluate this function for when x is equal to that not so nice number. All right. So L of 0.1 would be equal to 0.1 plus 1, which is 1.1. All right. And so it's easy to verify because all I'd have to do is type in e to the 0.1 power, and yeah, 1.1. It's 1.105, but 1.1 is a reasonable approximation for that. So that's not too bad. Right? But that's the concept of linearization. The next two things that we're going to go over, one is very quick and straightforward. Actually, they're both very quick and straightforward. The first thing that we're going to do is actually an algorithm called Newton's method. The second thing is actually only quick and straightforward because of what we just did with linear approximation. All right. So if I had to teach that one from scratch, it would take a while, but it'll be quick and straightforward because we've already done the heavy lifting. But Newton's method is a fun algorithm used to find the roots, but it involves finding a derivative. Yeah, I'm going to give you the short version in terms of the explanation as to the theory behind it, but it's pretty cool. So this right here on page 61 would be the long version. So we're going to skip over that. You can do this. It's interesting, but it's more of a kind of a lab than anything else. If we have time, we'll come back to it. But I wanted to take you to page 62. And right to, yeah, I'm scrolling around like crazy here. Right to where it says Newton's method. And you can see the notation here. It's pretty funky, but it's really the linear approximation model again, right? So what's happening, and I'll just take you back to a very simple function using, let me get rid of some of this extra fluff here. I'll leave the approximation error. All right. So let's say you just have a simple function, y equals x squared. I'll say x minus 2 squared plus 1. Minus 1, actually. It needs to have a root. All right. So you got a parabola, for example, and I have my tangent line here. Now, that point of tangency, depending on where it is, we know could represent a pretty good approximation for the value of y depending on x for the function, right? Where the idea is that if you plug into the tangent line equation as opposed to the function itself, you might end up getting a reasonable approximation of the function itself, right? But an application of this that's pretty cool is if we do that around the x-axis. Right? So we bring it down around the x-axis. That point of tangency could help us determine the roots of the function. Right? So what we would do is we would take our linear equation, so just L of x is equal to f prime of a times x minus a plus f of a. And instead of setting our original function equal to 0 and solving, which is how you would find the roots, so we would have some function f of x, so given y equals f of x, instead of saying f of x equals 0, we can use L of x as an approximation and let L of x be equal to 0. Because if the L of x is a reasonable approximation of the function itself, then finding the roots of the tangent line could give us a sense of what the roots of the original function are. And so in doing so, we would get 0 is equal to f prime of a times x minus a plus f of a. All right. And so I would solve this by subtracting off an f of a. So I'd get negative f of a is equal to f prime of a times x minus a. Then I would divide both sides by f prime of a. Which would, in effect, cause a cancellation. Sorry, I'm just going to delete that. This one looks nicer. We get a nice cancellation here. We get x minus a is equal to this ratio here. And then all I'd have to do is add a to both sides. But that run, or at least brings us to a little bit of an issue. And that is, if our linear approximation model isn't a good representation of the function itself, then you could be looking at something that's nowhere near the roots. All right. So for example, like in my Desmos, I have a pretty good tangent line if I'm looking for the roots, where if I solve by setting my tangent line equation equal to 0, my linear approximation equation equal to 0, I'll get the root because it's spot on. But if I have my tangent line somewhere over here, then by setting my tangent line equation equal to 0, I'm going to get a root that's nowhere near what the correct root is. Right? So what ends up being the case is we use what's known as an iterative process. I can barely say that term. An iterative process, which tells us that if we take a value and plug it into this expression here, right? And by the way, that's the general rule to some extent, but what we can do is make a recursive formula out of this, which calls on previous computations. So if I take the answer to this expression here, So simplify this, get an answer, and then plug that answer back into the expression and keep going. I'll get closer and closer to the true value, right? Because what it's going to do is it's going to inch closer and closer to the actual root, right? So what we end up with as a rule, just using the appropriate recursive notation, would be x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. Right? And it's a very easy process computationally to carry out. It's just kind of tedious. Right? So I'll show you in a sec, but really all it is taking our linear approximation model and moving some things around. But this notation allows it. You'll learn more about it in Calc 2, like recursive models and sequences and things of that nature. But what it's telling us that we can do is take a value, plug it in for x, simplify, get an answer, and then take that answer and plug it back in for x and do it again. All right. So there are instances in which Newton's method fails, but I'll get to that in a couple of minutes. All right. But what I wanted to do is carry out an example or two using this approach and show you just how manageable it is. But it takes a little doing because it's, like I said, a little on the tedious side. All right. So the examples here, they're kind of out of order. So I'm going to do number 5 first and then come back to number 4. But it's pretty straightforward in the sense that you'll have a function, that function will have a derivative, and then it's just a matter of making some substitutions. All right, so let me show you. If I have something like x cubed minus 3 equals 0, what that means is that we had some function f of x that was equal to x cubed minus 3. And that function f of x was set equal to 0 in order to get this equation. All right. So we have a function to work off. All right. So f of x is equal to x cubed minus 3. All right. So what I need from that is a derivative, f prime of x. Simple power rule, so 3x squared, not difficult. All right. When I want to create my recursive model, I'm going to have x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. And all that's telling me to do is replace each x value here, whether it's in the original function or the derivative, with an x plus n. So we'll get x sub n plus 1 is equal to x sub n minus x sub n cubed minus 3 over 3 x sub n squared. Right? Notation wise, it's not hard to write. I mean, you just want to keep your subscripts organized. It's knowing what on earth to do with this now that we have it. That's what makes it challenging. So what we can do is, and this is the beauty of Newton's method, if you have an initial value that you can, they call it a guess or an initial seed. It's kind of, I don't like that. It's more like it's a suspicion of the neighborhood of where you think the roots are. That's what you would let your x sub n value be, right? So what we would do is let initially n equal 1. Corresponds to x sub 1, which is some initial value for x that we think is somewhere in the neighborhood of the root of the function. Now, the benefit of accuracy here is that the closer you are to the root itself, so if you have a suspicion of where you think the root is, the closer you are to that, the quicker it'll be before you actually get to the answer. Right. So let's say, for example, I want to get to a 0 in my original function. So we already know that the answer is going to be the cube root of 3. Right? Cube root of 3 squared is 3 minus 3 is 0. So it's really just a matter of, do I know what the cube root of 3 is? Well, off the top of my head, no, but I got to imagine somewhere near 1. Right? Now, it's not going to be 1 because 1 cubed is 1. 2 cubed is 8. It's definitely closer to 1 than it is 8. So you could say 1, 1.5, something like that. But what we would do is start off with some value that we're comfortable with, plug it into this formula. All right. So I'm going to go with a 1. All right. This is an initial guess. Right, but it can't be just some random guess. If you're gonna make some random guess, that random guess could be like negative 13,000. You wanna have some reason for suspecting that the answer is gonna be somewhere around this value. Now, what most people do, just for full disclosure, they usually figure out the answer and then choose something that's pretty dang close to that. So probably 1.5 is a better guess, but I went with 1, so here we are. All right. So if n is 1, then my first computation would be x sub 1 plus 1 is equal to x sub 1 minus x sub 1 cubed minus 3 over 3x sub 1 squared. All right. With x sub 1 being equivalent to whatever my initial guess is, my initial guess is a 1. All right. So x sub 1 plus 1 is x sub 2. So I don't get to choose any more values after this. My second value is going to be dictated based off of the results of my first value. So 1 minus 1 cubed minus 3 over 3 times 1 squared, so 3. So 1 minus 2/3, all right? So 1 minus 2/3, oh, negative 2/3, sorry. So 1 plus 2/3 is 1 2/3. But we probably want to have that as an improper fraction. So 1 2/3. So that's going to be 5/3. So that's my x sub 2. All right. Since we know the answer is about 1.4, 1 2/3 is about 1.6, 1.67. That 1.67 is closer to 1.44 than 1 was. So we're moving in the right direction. So then what we do is we move on to the next n value. So x sub 2 plus 1. So I did 1 plus 2. Sorry, I'm just, no, it's 2 plus 1. I second guessed myself. All right, so that's going to be x sub 2 minus x sub 2 cubed minus 3 over 3x sub 2 squared. All right, so I would plug in my x sub 2 value now, and you see that this gets tedious and crazy, but it's really not so much a matter that you can get an answer as it is that you can follow the process. All right, so 5/3 minus, you see, I'm about to cube 5/3, so it's going to get nasty. 125 over 27 minus 3 over 5/3 squared is 25/9 times 3 is 25/3. All right, so the number, like I said, they're not very friendly. But then that's where the technology comes into play. You know, let the calculator do the work for you. All right. So what I tend to do is have just a demonstration, or I ask students when I ask you to do a question like this on a test, is just a demonstration of the process, right? So that's what's happening here. It's really not, again, as much about getting the answer as it is carrying out the correct procedure, because technology will do the work for you. That's, if I wanted the answer, I would just find the cube root of 3 and be done with it. It's a matter of carrying out Newton's method, right? So, but for the sake of brevity, I'll just pop this in here. So in fraction form, you get 331 over 225. But the idea is that we are now way closer to the correct answer than we were previously. We started off with an initial guess that was about 0.44 away from the right answer. Then after the first iteration, we were about 0.27 away from the right answer. Now we're about 0.03 away from the right answer. So you see, we're getting closer and closer to the right answer. And so if we were to carry, I mean, you probably have faith, hopefully, that if we carry out this process, then we would end up getting our correct answer eventually. So that's the idea. I'll do one more iteration. It's just so you can kind of get the point. But this is really all there is to it. There's really not much more. Right. So again, we're following this model. Well, it's really this model that was modified based off of our particular information. But we're looking at our n value. It started off as a 1. Then it became a 2. Now it's a 3. So x sub 3 plus 1 is going to be x sub 3 minus x sub 3 cubed minus 3, 3x sub 3 squared. I think we covered all the different ways in which one could write the number 3 in a sentence. We got them as subscripts, we got them as superscripts, we got them as coefficients. I get we don't have it as a the solution yet. Right, so that's them, but we're pretty close. Right, so in for every x sub 3, we'd have to plug in 331 over 225. Right, that's pretty nuts. Show us the Desmos trick for this. Oh, you want the Desmos? I knew you would. It's the kind of thing, I say this in some of my classes. I don't know if I say it in all of them. But people don't realize that they love Desmos until they realize they love Desmos. Because it's like, I don't need Desmos. It's fine. Like I can do all this stuff without it. And then you see something like this and you're like, all right, show me the Desmos shortcut because this is nuts. All right. So there really isn't much to the shortcut, but I'll show it to you in a second. All right. It's the kind of thing where you don't even really need a dedicated calculator for it. It'll just kind of work itself out. All right. So 331 over 225 minus 331 over 225 cubed minus 3 over 3 times 331 over 225 squared. And I don't know, also something else to consider. You really don't need, nice. You really don't need to wait for me to grace you with the Desmos shortcut. Hey, I gotta say, I'm fairly new to the Desmos community. There have been people that have done some way more interesting things with Desmos than I've done. I'm basically still trying to understand what they're doing. Right. So if there's a concept where you're thinking, you know what, I wonder if there's a Desmos approach for this, go ahead and Google it because odds are there is. right? The problem is if you're not familiar with the math enough to know what a good Desmos would be, then you might have to wait. But something like this, it's probably just a matter of having a quick look. So let me open a new graph here, because again, we don't want to do all this. Like this is crazy. So we had our original function, right? F of x. We typed that in. That was originally x cubed minus 3. All right. What we did was we took the x value and subtracted from it the ratio between the function evaluated at that x value and the derivative evaluated at that x value. All right. So let's do that. So, except I want to have the flexibility enough to change that x value any way I want. So I would type in a minus fraction f of a over f prime of a. And then throw in a slider for the a value. All right. Now, you may not recognize this, but when that a value, which defaults to a 1, whenever you create a slider, the default value is 1. It plugged in a 1 for a, and it gave me a 1.6 repeated, which in fraction form is 5/3. So it actually gave us the first iteration. All right. So it gave us this value here. All right. So then what I would do is take this number and plug it back in for a. So make my a value 5/3. And now it gives me the 331 over 225. So then I would take my 331 over 225 Now it's given up on representing it in fraction form, but it's going to tell us that this is approximately 1.4428. I'll say 1.443. All right. Once it gives up on giving it to you in fraction form, then you'd have to start typing in decimals. But if you're using a computer, it's copy paste. But I would type in, let me just jot this down real quick. I'll just do one more iteration. I would write in or type in 1.44281209.825. And then you could see here that it gives me yet another computation. Right. So I would know that x sub 5, if I needed it, would be approximately 1.442. So you see it's getting closer, it's actually settling in on a particular value. We call that convergence, right? So 3 raised to the 1/3, that's what it should be. It's not too far off from that, right? So we're pretty spot on. We just had to go out 5 iterations from the initial guess, right? But that's really all there is to it. So in terms of what you would do on Desmos, it's really just putting in the formula just in terms of a rather than x sub n, right? So I'll even jot that down for you. So in Desmos, input function then a minus f of a over f prime of a. And then once you do that, you keep re-inputting your answer for a. Until you're until you arrive at the answer. All right. So it's really pretty straightforward when it comes to that. You too, Matt. You're still here. All right. So when it comes to something like part B, you have all this stuff here, which is really focusing in on the notation. If you just need to cycle through the values, it's really not too bad because we know f of x is x to the fourth minus 5x plus 2. If I need to report f prime of x, that's 4x cubed minus 5. If I need to give the rule, which is often the case, following this model here, I would write x sub n plus 1 is x sub n minus the original function replacing all of the x's with an x sub n. So x sub n to the fourth minus 5x sub n plus 2 over 4x sub n to the third minus 5. And then it's just a matter of carrying out the iterations in whatever way makes sense, right? So I would let my x sub 1 be whatever I think is close to the correct answer, but sometimes I have no sense. So if that's the case, then I would go right to the calculator, pop in the function. We're not expecting it to be a clean answer, otherwise we wouldn't be approaching it this way. All right, looks like we have two answers here, but it looks like if I choose a value near, let's see, this, I mean, you could really cheat and get the answer. So I could say, let my first x value be equal to 1/2. And then I would just kind of pretend I didn't know the correct answer, at least initially. Slide my slider. Come on. Eventually you give up and just start typing it, which is what I'm doing now. Oh, wrong thing. Yeah, it gives me a result of negative 29 over 88. So negative 29 over 88 gives me a negative 0.4045. So I would type this number in. So I just kind of jotted down to myself. And then type it in. Just because I'm using a touchscreen, it's some pain to try to copy paste. But if you're using a keyboard, it's easy enough. All right, and so we're looking at about 0.405, negative 0.405. Oh, you know what it was? I was actually looking at the wrong side of the axis. I should have put a negative 1/2 to get started, but I didn't. So here we are. But negative 0.4054 is really where we should be. And so even though I started off with a 1/2, it got me there pretty quickly. All right. But because there's two roots here, I'd also have to select some value to start off with. So I got to do the process again, some value to start off with that would get me to the other root. And so that other root is at negative 1.54. So I would do x is equal to, let's say, negative 3/2. So negative 3/2. So that would be my first entry. My second one, negative 211 over 196. 136, sorry.
What?
Wanted it to be 196. So negative 211 divided by 136. Now we're stuck in decimal world. X of 3, approximately negative 1.5478. All right. And that's really what we should have. So we're right there. So after 3 iterations, we got our answer. Right? So that's pretty cool. All right. So that's really all I would ask you to do for Newton's method. I mean, it's a fair amount, but like fortunately the calculator does a lot of the heavy lifting for you. All right, so we just have to talk about one more thing. And so we're not going to worry about solving systems of equations and stuff like that with Newton, right? All this stuff. But we're going to talk about differentials, which is a pretty interesting topic also. In fact, we're getting into the more interesting stuff in the course. Differentials can be used in a variety of different ways, but you might have heard of a course called Differential Equations. Differentials they work hand in hand with those concepts. So whenever you create or find a derivative, you're in fact finding the equation associated with differentiation, which is known as a differential equation. All right. So what we're going to do is the building blocks of that just work on the notation, but I'm also going to show you how you could use differentials to approximate certain values, right? But when it comes to writing an equation in differential form, it's very simple. All you're doing is taking the derivative all right, the derivative, this is a differential equation. All right. Now, dy, if I multiply both sides by dx, because dy dx is really at its heart a ratio. A ratio is a fraction. If you want to solve a fractional equation, one way to do it would be to multiply both sides of that equation by a common denominator. So the denominator here would be dx. All right. Actually, I'll show that in a separate step, just because I have that notation there, or annotation, I should say. Get out of here. So I'm going to multiply both sides by dx. And so what we end up with here is known as a differential form of the differential equation. I don't know how familiar people are with antiderivatives, but you will be in the next unit. But this is the building blocks, or building block, one of them anyway, of an antiderivative. All right. And so conceptually, what we're looking at is kind of cool, because if I have some graph, and I don't know what 5x to the fourth plus 37 looks like particularly. I know it's a fourth degree polynomial, and I know it's got a leading coefficient that's pretty big, so it's going to be skinny. Its constant value is 37, so it's going to be pretty high up on the y-axis. But aside from that, shape-wise, I'm not really 100%. But what I can do is just kind of rough out a quick sketch of it. Sorry, that kind of took off on me. Something along those lines. Now, what we're talking about when we say dy dx, that's a rate of change. All right, change of y, change of x, instantaneous rate of change, all these different things, they all mean the same thing. But if I'm focusing in on a single point, what I'd be doing is really zooming in on that and saying that there are 2 points on the graph that are infinitesimally spaced. All right. That infinitesimal spacing horizontally is known as dx, vertically is known as dy. All right. So that's what dy dx has meant for us. All right. Now, I'm going to put that aside for a second. Look at the same function, but now we're changing the perspective a little bit. Because the 5x to the fourth plus 37, that's some function f of x or y. All right. Any coordinate in space is defined by its horizontal distance and its vertical distance, as in the distance from the y-axis followed by the distance from the x-axis. So if I'm focusing in on, let's say, this point right here, same idea. It would have some distance x corresponding with some distance y. All right. What this is saying, that differential equation, but in differential form, is saying that there is a height associated with the y value and some horizontal distance, again, that we call dx, by multiplying those two together, what we're getting is an area. That area, let me do that in a different color. That area is equal to dy. So what it's really telling us is that dy, even though it represents an infinitesimal vertical change, it's also going to represent something completely different. All right. All based off of just the way we look at an equation. Right. Because dy over dx told us one story, but dy being equal to the product of the function, or the derivative function, sorry. I apologize, I meant to put a f prime here and a y prime. Notation. All right, so that is equivalent to an area. And that area is going to tell us something more when we get into it in the next unit. All right. So, I mean, I guess it could be some function f of x, but these are supposed to be derivatives. Apologies for that. All right, so the second, third, and fourth examples here, they're really just going to tell you the same thing, which is take the derivative and just slide the dx over to the other side. Like, for example, number 3, dy dx would be equal to secant squared of 2x times 2. And so if I multiply both sides by dx, I get dy is equal to 2 secant squared 2x dx. That's all this stuff is asking us to do. What I wanted to show you is how we could use this concept of a differential to help us approximate values, right? Because that's what this part of the unit's really all about, developing approximations. And so we use linearization, we use Newton's method, and now we're going to use this concept called differentials to help us get that job done. Okay, so let me just show you. It'll take a couple of minutes, literally a couple of minutes. It's very quick, but and all of this stuff here, this is all what I was just explaining. All right, so you can read through that if you like, but we're only going to focus on this, the estimated change, also known as approximated change. All right, so I'm just going to change the instructions here. So all we're going to do is find, like I said, the estimated change. So you can see here that it's using, it says df equals f prime of a dx, but that's really just the differential form of a differential equation, just what we were doing on the previous page. All right. So you could also look at it, and I'll show you a slightly different variation of it. If I were to say y, this might be a little nicer. Y is equal to f of x. If you take the derivative of that, you get dy over dx is equal to f prime of x, which is what we did on the previous page, just in full notation form. And you just multiply both sides by dx. And you get dy is equal to f prime of x dx. All this is saying is that we would do it additionally at a particular value of a. Right? So if x is equal to a, then dy would be equal to f prime of a dx. Right. So that might be a more appealing version of the formula. Right. So it all depends. So actually, I'll use this one, and I'll even take that as a typo. So let's say we have this function x squared plus 2x. Right. If I were to plug it into this form, so that's really all we would need to do. I would have to determine f prime of x, which is 2x plus 2. The estimation would be dy is equal to 2x plus 2 dx. Now they told us a couple pieces of information. They told us the a value and they told us the dx value. All right. So if I determine this at x equals 0, so the a value is equal to 0, I would get dy is equal to 2 times 0 plus 2. They also told us that dx is equal to 0.1, so I'd multiply that by 0.1. And what that'd give me is 2 times 0.1, which is 0.2. All right. So it's an answer. It's the correct answer, which is ideal. But it doesn't really scream, oh, I see what this is for. You know, so it's not 100% obvious, but let's go back to the original function. F of x is equal to x squared plus 2x, and then pop in the 0 for x. All right, so f of 0 is equal to 0. That's no surprise because if I plug in a 0 for x, that's fine. Now, if I plug in a 0.1 for x, I'd get a 0.21. All right. So what's happening here, and it's kind of strange to think about, but what's happening here is that we have some function f of x and an a value that's indicated. All right, this is a given a value, corresponds to a point on the graph. Zero, 0. All right, but I'm going to type that in as 0, comma f of 0, because it's not always guaranteed to be a y value of 0. It's just in this case it's 0 because that's what you get when you plug it into the function. All right. So this is our a value. lowercase a value. All right. Now, what they're telling us to do is just smidge over 0.1 to the right and figure out the y value corresponding to that. All right. So what this is saying is increase a by 0.1 and determine the y value. If I increase a, that a value by 0.1, it would become 0 plus 0.1. If I wanted to find the y value that goes along with that, along being the word of the day, along, I would evaluate my function at 0 plus 0.1. Right? And that would give me a y value of 0.21. What this process will do is determine the change in y corresponding with this change in x for that function, for that given function. All right, it'll tell us what we would have to increase this y value by based off of that horizontal change. All right, so in the next example, you see the a value is equal to a 1, so it's a little bit different. So we would do the same process. F prime of x would be 4x to the third. All right, so I would be looking at dy equal to 4x cubed dx. All right, now this is at the a value of 1 with the dx value of 0.01. All right, so dy when a is equal to 1 and dx is equal to 0.01 would be 4 times 1 cubed times 0.01. All right, so it's 4 times 1, which is 4, and then 0.01 is 1/100th. So 1/100 times 4 is 4 100ths, which would be 1/25. All right, now if I were to evaluate f of 1.01, I'm probably not going to get 1/25. Right? So, and what I mean by that is, again, f of a is the same as f of 1, which would be 1 to the 4th power. But this is telling us to increase a by 0.01 and determine the y value. All right, so that would be the same as saying f of whatever the a is plus the dx, which would be f of 1.1, 1.1 to the 4th power is 1.4641. Right, that's nowhere near 1/25. All right, but what this is telling us is the deviation between, oh, sorry, what, 1.01, thank you. I didn't even read the chat, but I know that's what it must be. 1.040641. Right, so this is what the value should have been. Now, what this number is the value that we would have to add on to the result of f of a in order to get an approximation for this value. All right, so we add this to f of a. So f of 1 plus 1/25th. So that's our f of a value plus our dy is going to give us our approximation, which would be 1 and 1/25th, which is 1.04. Right, so it's a reasonable approximation for that particular value. right? The 1.04641, we came up with 1.04. There, the real answer would round to 1.05. We came up with 1.04, but in the grand scheme of things, it's not too far off, right? So that's really where we're at with that, right? So it's really not too crazy, right? But then I'm going to skip number 3 because that's probably a little too much. But number 4, estimate the value of 49.5 using this method, right? And it's kind of cool because we did this with linear approximation, and so now we're going to do it with differentials. We could have even done it with Newton's method, but I thought that would have been going a little overboard. But same idea as the setup for linearization. If I assume that there's some function f of x that has or has been evaluated to give us the 49.5, okay, then that function must have been the square root of x, all right? But what we would do here, and again, it's the same process in that we're going to choose a nice number. So the nice number would be a perfect square near 49.5, which is 49. But then what we do is we figure out dx, which would be the distance between that nice number and the given value. All right, 49.5 minus the 49, that's the deviation. All right, so the deviation in x. All right. So unfortunately, you're on the hook for all of the methods. So they all have value for different reasons. We're using them all to kind of evaluate the same type of problem, but yeah, they're all necessary. Oh, I wish. Honestly, if it was a matter of us having a choice, I would have already made that choice and eliminated all the unnecessary stuff. But as they say, it is what it is. All right, so f of x is equal to x to the 1/2 power. So f prime of x would be 1/2 x to the negative 1/2 power. And so using this idea, we would say dy, for quality d, is equal to 1/2 x to the negative 1/2 dx. And so to get our approximation value, all we'd have to do is evaluate dy when x is equal, when x is equal to the a value, which is 49, and dx is equal to 0.5. So that's going to be 1/2 49 to the negative 1/2 times, this could be thought of as 1/2. So 1/2 times be 1/7, because you flip the 49 over, it becomes 1/49 to the 1/2. Square root of 49 is 7. That's one of the reasons why we selected 49 as the nice number, times 1/2, and we get 1/28. All right. Now 1/28 is not the square root of 49. What that is what you would get as it's the deviation in y corresponding with the deviation in x. So we know that f of 49 would be equal to 7, because that would apply 49 into the square root model. So just like what I said up here, if I take f of a and add to it dy, in this case, I would get square root of 49, add to it 1/28, and I get 7 and 1/28. And that is something that we can put into Desmos and just do a quick double check. 49.5 is a smidge more than 49. So I'd expect my square root to be a smidge more than 7. So 7 plus 1/28 versus the square root of 49.5. All right, so pretty spot on in terms of an approximation. All right, so there we go. Anyway, that's it. That's it for the unit. I'm going to stop the recording.